So you can see I've set up my two ellipses with the correct parameters, and now I'm going to subtract basically the two circles to give me the range that I want. And we're going to set up diffusion. Then we're going to go to boundary conditions. We're going to do boundary mode. Then all of the inner ones need to be Dirichlet boundary condition of 2. Right, so we're going to specify boundary. We're going to set this boundary to 2. Then all the outer ones need to be of Dirichlet boundary 1. So we're going to do Dirichlet boundary 1. Then we're going to initialize our mesh. We're going to refine our mesh. And then we're going to create it. And you can see here, diffusion, we can also find the flux, right? And this is the flux right here. Okay. And then we can go back here, go to concentration. And now, so what I did is I plotted this and exported it using mesh, right? Exported both. And after I exported them, I kept on refining the mesh and serving the values, saving the values in p's. And then here I converted the x and y into polar coordinates and recorded basically the diffusion value for each. And so when we run it, we see that increasing resolution, giving us better value results, closer to the end resolution. So now for problem 2, we can see that we have set up an ellipse and we're going to run it. And we see that we form two ellipses. We're going to subtract them from one another in order to get our answer. Then we set this to diffusion. Then we have our boundary conditions. These all the inner ones need to be Dirichlet boundary conditions, right? Boundary, and they need to be 2. And then all the outer ones here need to be 1, Dirichlet 1. Right, so now we initialize our mesh, we refine our mesh, and we solve it, and we see once more the gradient. We can also find our flux, but now we export it. So we're going to export our mesh, right? We're going to export our solution as well. And now that we've exported both, what we're going to do is we're going to plot them. So I've already set up a plot for it, similarly to the here cartpool. So we run it, and you can see here as we're going on from the radius, we can see that there's a lot of fluctuation in the diffusion. Thank you. So here I'm solving problem 2C, and I have a rectangle. So I'm going to set the height significantly larger than the width. So the height is going to be 10. The width is specified 1. Then we can just set it to be in the corner. Okay, done. And now what we're going to do is we're going to set it to diffusion. Then we're going to go to PDE, and we're going to set the source volume to UX multiplied by UI basically being the gradient here is what we're doing. And then we're going to have our boundary. We're going to have then our boundary conditions, right? And basically this is going to be a Dirichlet boundary condition of 2. This is going to be of 0. And then right here, these two are going to be Newman boundary conditions because they don't really matter. So once we've done that, what we're going to do is we're going to go to solve parameter and make sure that it's use linear solver and Jacobian full. So once we've done that, we can initialize our mesh, we can refine our mesh a little bit, and we can go for it. And we see the diffusion, the concentration profile here. We can also get the flux. Here's the flux. So now going back to the concentration. So what I did similarly to what I did in the first one, I exported the mesh and exported the solution. But I did this for increasing that max size T array, right? So increasing mesh, and then I plotted all that along with the analytical solution using using this right here, right? This is the analytical solution, and this is the actual solution. And so plotting it, you see this is the analytical part, and this is the numerical part. And we see increasing basically resolution, helping us get closer to the analytical solution and getting us more